On November 15th, 2023, a then 89-year-old New Zealander dropped a scientific bombshell. Roy Patrick Kerr submitted a paper asserting that there is no proof that the catastrophic collapse of a massive star to form a black hole results in a point of infinite density, a contradiction of the claims made by Penrose and Hawking that singularities are inevitable. Kerr says point singularities do not exist. He adds, they did not prove what they thought they proved. Such an assertion, coming from anyone else, might be safely ignored. But Roy Kerr isn't any old theorist. You see, in 1963, some 47 years after the famous Schwarzschild solution was found for Einstein's equations for gravity, Kerr dropped his first bomb. At just the age of 29, Roy Kerr found another exact solution to the Einstein field equations. He found the description of the irresistible tornadoes of spacetime that surround rotating black holes. And he dropped this bomb in a most stealth-like manner. You see, Kerr presented his findings at the first Texas Symposium on Relativistic Astrophysics, held in Dallas just 4 weeks after the assassination of President John F. Kennedy. And the topic at hand were quasars, objects that would pump out 100 times the light emitted by an entire galaxy, yet from a volume smaller than a solar system. During his 15-minute presentation, people in the audience talked, read newspapers, and generally ignored him. No one realized what he was doing. He was proving the quasar mystery. You see, the extraordinary luminosity of quasars come from the matter heated to incandescent levels as it swirls onto a spinning black hole, with a mass of 1 billion or even tens of billions times that of the Sun. In 2020, it would be Roger Penrose that would win the Nobel Prize for his work on black hole singularities. But in 2023, it was Kerr that argued it is extremely unlikely point singularities exist and go against known physics. Penrose and Hawking made some dodgy assumptions. Singularities don't exist. So what was Kerr's advance? What was his reasoning? In the real universe, the ideal case of having a mass with no rotation to it isn't exactly a good physical model for reality. Consider that 1. There are many masses in the universe. 2. Masses over time will gravitationally attract one another. 3. Matter will clump together in non-uniform ways. 4. Non-uniform masses moving relative to one another will not only gravitationally interact, but they'll exert a torque on each other, causing rotation. And as rotating objects of mass collapse, their rotation rate increases due to the conservation of angular momentum. So Kerr argues most physical black holes are rotating ones. In the Schwarzschild solution, there exists a point singularity and an event horizon which occurs at what is called the Schwarzschild radius. This is a static, non-rotating black hole. It is a structure which is simple and unrealistic. Nature is not static. The Kerr black hole looks and behaves extremely differently. Instead of a single spherical surface describing the event horizon at a point-like singularity at the center, the addition of rotation causes there to be several phenomena that are not apparent in the static case. You see, in the Kerr solution, there are 2 horizons. Since the Kerr case is a quadratic, we get an outer horizon and an inner horizon. The inner horizon being an event horizon. Instead of the event horizon marking a location where the time-like component of the metric flips sign, there are now two surfaces that are different from the inner and outer event horizons, and they are called the inner and outer ergospheres. They delineate those locations throughout spacetime, and they harbor a ring singularity, where the angular momentum that is present smooths out that singularity into a one-dimensional surface, a ring, with a rotational axis that is perpendicular to the center of the black hole's rotation. One recalls the Schwarzschild metric. Here, R sub s stands for the Schwarzschild radius. And that radius is given by 2gm over c squared. We can simplify this expression by using d omega squared to equal d theta squared plus sine squared theta d phi squared. And at r equals 0, this produces a point singularity. So we get an event horizon at the Schwarzschild radius, and at r equals 0, a point singularity. Now if we introduce some angular momentum, some spin to the black hole, we get the Kerr metric, which describes the geometry of spacetime in the vicinity of a mass, m, rotating with angular momentum, j. The line element for proper time is given then by ds squared equals negative c squared d tau. And in the Boyer-Lindquist coordinates, the Kerr metric is as follows. And one will notice a few extra terms in here relating to the rotation. This metric also has a cross term. Capital sigma is given by r squared plus a squared cosine squared, and delta is r squared minus rsr plus a squared, and a is given as the angular momentum j over mc. We can simplify this expression by choosing a certain set of units. That is, in geometrodynamical units where g and c are set equal to 1, the Kerr metric takes on a more simplified form to look like this. And again, we have a cross term here, which we'll explain in a moment. Capital sigma, delta, and a are all the terms that are related to the rotational aspect of the Kerr black hole. If we dissect some of these new terms here, we have the sigma term, which is r squared plus a squared cosine squared, and this term encodes how the geometry depends on both the radial distance r and the polar angle theta. When a is equal to 0, sigma reduces to r squared and the Kerr metric reduces to the Schwarzschild solution. When a is not equal to 0, meaning that there is some spin, then sigma varies with the latitude theta, that is the geometry near the poles at theta equals 0 and pi, is different from that which exists on the equator, theta equals pi over 2. And this leads to the Kerr spacetime being axisymmetric, not spherically symmetric. You see, Sigma reflects how the radial distance becomes angle dependent in the presence of spin. And what we get is a ring singularity, which is the true singularity in the Kerr spacetime, and it occurs on the equatorial plane. The ring singularity has a radius of a. So sigma controls the strength of the curvature like a warped radial function. So what does delta represent? Well, delta is a radial function, and it governs the horizons of our black hole. In fact, the roots of delta equals 0 give the locations of the event horizon on the outer and the inner portions. The outer horizon is usually referred to as the event horizon, where the inner portion horizon is called the Cauchy horizon. These horizons are designated by R plus and R minus respectively, and the roots are given to be equal to m plus or minus the square root of m squared minus a squared, R plus being the outer horizon and R minus being the inner Cauchy horizon. Now, for non-rotating black holes, that is for a equals 0, delta reduces down to the Schwarzschild metric solutions, where r equals 0 is a point singularity and r equals 2m gives us the Schwarzschild radius. So it defines the location of what we call the null surfaces, and the radial metric component GRR given by delta over sigma affects the infall of items into the black hole. Again, this affects the off-diagonal elements as well, giving rise to something called frame dragging. So let's examine the behavior of delta by region. You see the region outside the event horizon, which is R+. Space-time behaves normally, and we can calculate the area, the surface area of the black hole to be given to be 4 pi R plus squared plus a squared. Inside the surface horizon defined by R minus, inside the Cauchy horizon, determinism breaks down. Strange causal structures begin to emerge. The region that exists between R plus and R minus have causal structures being inverted. That is, radial coordinates become time-like. Time becomes space-like. And this is when delta is negative. The radial direction becomes time-like means that any object entering this region, called the ergosphere, must move inward towards the center. The ergosphere, we have the time component given by this to always be positive. Objects cannot remain at rest relative to infinity. The frame dragging is so intense, objects must co-rotate with the black hole. Space-time itself drags you with it. However, it is possible to escape the ergosphere. If a squared is greater than m squared, then delta is equal to r squared minus 2mr plus a squared and has no real roots or no horizons. It exposes the ring singularity, and naked singularities are typically not allowed by the cosmic censorship theorem. Delta determines the causal structure of the Kerr spacetime. It encodes how and where horizons will appear, and it helps us define the frame dragging itself. If the inner surface, R-, is equal to the outer surface, R+, this occurs the purely radial component goes to infinity. Solving the quadratic equation, 1 over this component, which would go to 0, yields the solution R horizon is equal to the Schwarzschild radius plus or minus the square root of r squared minus 4a squared all over 2, given by the quadratic formula, and in the natural units this simplifies to 1 plus or minus the square root of 1 minus a squared. So in comparison, while the Schwarzschild metric event horizon is such that the purely temporal component GTT switches sign from positive to negative, in the Kerr spacetime that happens at a different distance. Solving the quadratic equation for the time component GTT equals 0 yields the solutions for the event horizon by the quadratic formula. Or in natural units again, 1 plus or minus the square root of 1 minus a squared cosine squared. Due to the cosine squared term under the square root, the outer surface represents a flattened sphere, and it touches the inner surface at the poles of rotation. That would be at theta equals 0 or pi. This is where we get the axisymmetric form of the Kerr solution, and as the spin, the angular momentum, becomes greater, we see the sphere's ergosphere and the horizons being clearly delineated. Now, of course, if you increase the mass greater than the A value, then you get something that is more closely resembled to the Schwarzschild radius. The total mass equivalent, m, the gravitational mass, of the body, including the rotational energy, and its irreducible mass, m irreducible, are related by the following equation. So m squared is equal to m irreducible squared plus j squared c squared over 4 m irreducible squared g squared. You are now entering the ergosphere. If we write the metric out in its formal component form, it looks like this. This emphasizes the metric tensor terms. This metric is equivalent to a co-rotating reference frame that is rotating with an angular speed omega that depends on both the radius and the co-latitude theta, where omega is called the killing horizon. And it's given by this expression. Thus, the inertial reference frame is entrained by the rotating central mass to participate in the rotation. And this is what we mean by frame dragging. Although the Kerr solution appears to be singular at the roots of delta equals 0, these are just coordinate singularities. And with an appropriate choice of new coordinates, the Kerr solution can be, well, smoothly extended through the values of r corresponding to these roots. A future directed time-like curve can start in the exterior and pass through the event horizon. Once having done this, the r coordinate now behaves like a time coordinate. So it must decrease until the curve passes through the Cauchy horizon. Inside the Cauchy horizon, you see, there's a region inside the Cauchy horizon called the anti-universe. Once you cross the inner Cauchy horizon, the radial coordinate r continues to decrease, even becoming negative. This anti-universe region has some peculiar properties. At r equals 0, the feature arises in the Kerr spacetime, a ring singularity. This Kerr singularity is not a singular point, but a ring lying in the equatorial plane at theta equals pi over 2. And this ring singularity acts as a portal to a new region of spacetime in the disk lying within the ring. The inner horizon harbors the ring singularity, where new pieces of spacetime exist. Within the region inside the singularity, we have two asymptotically flat regions connecting a new part of the universe. Now, if we avoid the equatorial plane where the ring singularity lives, we can smoothly continue the coordinate r to the negative values. This region with r negative is interpreted as an entirely new asymptotically flat universe. And again, it's often called the anti-universe. So for negative values of r within this anti-universe, it also has something called negative ADM mass, which can be thought of as the total mass energy of the spacetime as measured at infinity. A negative mass is a highly unusual concept in general relativity, and its physical interpretation is still under debate. Closed time-like curves, or CTCs, and the Cauchy horizon. Within the anti-universe, an even stranger phenomenon occurs. The metric component g phi phi can change sign, specifically g phi phi given by this expression. When g phi phi becomes negative, the coordinate phi becomes time-like, and a linear combination of the coordinates t and phi become space-like. This leads to objects being able to travel back to their own past, violating causality. Strange things might happen in the anti-universe. Now, the boundary where g phi phi changes sign and the closed time-like curves first appear at the Cauchy horizon, defined by the condition where g phi phi is equal to 0, this gives the following expression. And thus the Cauchy horizon acts as a boundary beyond which the fundamental notions of cause and effect break down. The anti-universe of the extended Kerr metric is a perplexing theoretical construct. It presents a scenario with negative mass, reversed time orientation, and the possibility of time travel through closed time-like curves. While the physical reality of the anti-universe remains uncertain, its study provides valuable insight into the nature of space-time, gravity, and the limits of our current understanding of the universe. All right, let's review. The non-zero components of the Kerr metric tensor are given here: GTT, GT phi, GRR, G theta theta, and G phi phi. The GT phi term is the off-diagonal term. It has to do with the spinning aspect of the black hole. Now, you'll notice that sigma and delta also appear in the GRR and the G theta theta term because the radial component and the angular components are affected by the spin of the black hole, creating a flattened sphere. Here you can get a more intuitive idea of what these terms mean within the metric tensor. The coordinates in the Boyer-Lindquist form have t as time, as measured by a distant observer, r is the radial coordinate, theta is the polar angle, and phi is the azimuthal angle. The gravitational time dilation again is given by the GTT component, where as r goes to infinity, GTT goes to -1, giving us a flat spacetime. The special surface, the ergosphere, at GTT equals 0, and inside this surface, time and space swap roles. Negative GTT is the fact that time becomes space-like, meaning that you can't remain stationary within the ergosphere. GT phi. This is the frame-dragging term. It means that the spacetime itself is rotating. You cannot resist being pulled around the black hole. Even if you try to stay stationary, you will be forced to rotate. This is why the Kerr black holes are said to be dragging the inertial frames with them. Any object near it will get twisted in the direction of spin. The GRR component given by sigma over delta. This controls the radial distance metric. It becomes infinite at the horizon where delta goes to 0, and it signals the presence of a coordinate singularity. In other words, this indicates how the radial distance will stretch near the black hole. The g theta theta term, which is equal to sigma, measures the polar angle distance, similar to r squared in spherical coordinates, but deformed due to spin. And the g phi phi term measures the azimuthal distance around the rotational axis. It includes effects of frame dragging, and the black hole's angular momentum, a, gets significantly warped near the event horizon and the equator. The special surfaces that appear in the Kerr spacetime are the event horizon as r+, given when delta is equal to 0, and the Cauchy horizon, r-, also given when delta is equal to 0, and the ergosphere, when the time component goes to 0, we get the region in the ergosphere to be given here by m plus or minus the square root of m squared minus a squared cosine squared, where stationary observers cannot exist. They are dragged along with the rotation. The physical implications are that frame dragging is any object near the black hole will be forced to co-rotate. This leads to the possibility of energy extraction through something called the Penrose process, and also effects called the lens-Thirring precession. Two horizons, unique to rotating black holes, appear, and between them lies a region where the predictions from general relativity break down or become extreme. The ring singularity instead of a point singularity exists in a ring-shaped region within, on the equatorial plane. Roy Kerr is a maverick. In 1963, he dropped his first bomb, and in 2023, he dropped his second bomb. And while still in his 90s, Roy Kerr still challenges our notion of what physically exists in the most extreme cases of space-time spinning. And within that spinning space-time, a whole new universe, a pathway to the unknown. No one really knows what happens if you pass through the ring singularity. What would you see? We may never really know whether point singularities or ring singularities exist, or whether they harbor wormholes to other anti-universes. But until then, I want to thank you for watching. I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.